Hello class! So we will now proceed to the second part of our discussion about torsion here in mechanics of deformable bodies. So for this discussion, students must be able to compute the shear stress and angle of twist of solid non-circular shafts and thin wall tubes due to applied torque. So let's start our discussion. Okay, so previously we talked about torsion in circular shafts. Okay, so everything that we talked about in that discussion is for circular shafts. So now here in our discussion, we are now going to discuss torsion in solid non-circular shafts. Okay, so shafts that have a non-circular cross-section are not axisymmetric, unlike circular cross-section. Axisymmetric, meaning to say, it exhibits symmetry, no, around its axis. If it's not axisymmetric, so it doesn't exhibit symmetry, okay, around its axis. So here, class, no, their cross sections will bulge or warp when the shaft is twisted. Okay, so if you're going to recall, no, in torsion in circular shafts, no, if it is deformed, okay, so the cross section of that circular shaft, okay, it will remain a circular cross section. Okay, it will not warp, no, it will not bulge in or bulge out. Okay, but here in non-circular shafts class, no, once it is twisted, once there is an applied torque, no, to this types of shafts. Okay, so what happens is that their cross sections will bulge or warp, okay, when the shaft is twisted. Okay, so evidence of this can be seen from the way grid lines deform on a shaft having a square cross section when the shaft is twisted, as shown in this figure. So as you can see here, this is the original or the undeformed shaft. Okay, so its cross-section class is square. Okay, so upon application of this torque, so this shaft will be twisted, and what will happen, class, is that as you can see here, no, the lines here, no, from the original shaft, okay, once it is twisted, class, the straight lines, okay, it becomes deformed. Okay, so it becomes distorted. Okay, so also class, its cross section, no, as you can see here, class, no, it warps. Okay, it also bulges in or out. Okay, and it also change in its shape. Okay, so as you can see here, class, no, it's no longer a square cross section, right? Unlike in circular cross section, no, it will still remain a circular cross section even if it is twisted. Okay, so here, class, this is different. Okay, and as a consequence of this deformation, the torsional analysis of non-circular shafts becomes considerably more complicated, and we will not consider that, no, in this discussion. Okay, so I will introduce to you formulas that we can use, no, to solve such types of shafts, okay, for torsion. Okay, so let's continue. Okay, so the results of the analysis for square cross-sections, along with other results from the theory of elasticity for shafts having triangular and elliptical cross-sections, are reported in Table 5-1. So these are already established formulas, class, no, for solving the maximum shear stress and the angle of twist, no, for shafts with cross-section square, equilateral triangle, and ellipse. Okay, so for the maximum shear stress for square cross-section shafts, okay, so the formula is 4.81 T over A cubed. Okay, where in T here, class, this is the internal torque. Okay, so this is the internal torque, and then A here, class, is the length, no, of the sides of the square. Okay, and then for the angle of twist, this is 7.10 times TL over A to the fourth over G. We're in L here, class. So this is the length of the shaft that we are, wherein we determine the angle of twist. And then A to the fourth, and then G. Class, G here is the modulus of rigidity or shear modulus. Now, for equilateral triangle, class, equilateral triangle, meaning to say, triangles having equal sides. Okay, so this is only applicable, class, no, for triangles having equal sides. Okay, so class, for the maximum shear stress for this cross section, okay, so this is 20T over A cube, and for its angle of twist, this is 46TL over A to the 4th G. Okay, now for ellipse, okay, so for ellipse class, the maximum shear stress is 2T over pi AB squared, wherein A here, class, is this side, and then B class here is this. Okay, so class, for its angle of twist, so this is A squared plus B squared TL over pi A cube B cube times G. Okay, so in all cases, the maximum shear stress occurs at a point on the edge of the cross-section that is closest to the center axis of the shaft. So in this table, class, these points are indicated as dots. So these are those dots. Okay, so also, class, given here are the formulas for angle of twist. Okay, and then by extending these results to a shaft having an arbitrary cross-section, it can also be shown that a shaft having a circular cross-section is most efficient, since it is subjected to both a smaller maximum shear stress and a smaller angle of twist than a corresponding shaft having a non-circular cross-section and subjected to the same torque. Okay, so this is the reason, class, why in most practices in engineering, no, we opt to use shafts having circular cross-sections. Okay, because it is most efficient. No, it is the most efficient cross-section. Okay, so class, we are going to prove that, no, in our computations here in our sample problem. So we will prove that, no, that circular cross-section shafts, no, are the most efficient types of cross-section for shafts. Okay. Okay, so we already know the formula, no, for the maximum shear stress and angle of twist for square, for equilateral triangle, and for ellipse. Now, for rectangles, no, let's say for the rectangle in this figure that carries torque T, so results obtained by numerical methods determine that the maximum shear stress and the angle of twist are given by this formula. Now, so for the maximum shear, so this is equal to T, okay, over C1 A B squared, wherein A here, class, no, so that is the longer side, okay, of the cross section or of the rectangular cross section, okay, and B, that is the shorter side. Okay, and now for the angle of twist, so this is TL over C2 AB cube G. Okay, so here, class, no, in this formula, G is the shear modulus. Okay, and again, as shown in the figure, for A and B, class, no, so A, this is always greater than, okay, or equal to B. Okay, so that's always the A here, class, this is always the longer side, okay, or longer dimension in the rectangular cross section. Okay, so here, class, no, L is the length, okay, of the shaft that we are considering. And class, C1 and C2 here, these are coefficients. Okay, and these coefficients, okay, depend on the ratio A over B, which are listed, okay, in this table. So these are the table, this is the table for the values of coefficients C1 and C2. Okay, so to solve for this C1 and C2, class, now we have to solve first or determine first, no, the ratio A over B. So again, class, A is always greater than B, ha. Okay, so once we already determined, okay, the ratio A over B, class, now we are going to look for that ratio here, class, and the corresponding value of coefficients will be this and this. Okay, so class, in cases wherein the value of the ratio A over B, no, is not exactly located, no, at these points, no, so what we're going to do, class, is we are going to apply linear interpolation. Okay, so to solve for its corresponding C1, coefficient C1 and C2. Okay. Okay, so let's start solving sample problem number 1. The 6061T6 aluminum shaft shown in the figure has a cross-sectional area in the shape of an equilateral triangle. So this shaft class, no, this has a or an equilateral triangle cross-section. Okay, so determine the largest torque T that can be applied to the end of the shaft if the allowable shear stress is 8 kSi and the angle of twist at its end is restricted to theta is equal to 0.02 radian. How much torque can be applied to a shaft of circular cross-section made from the same amount of material? Okay, so what we're going to solve here, class, will be the largest torque T, okay, that can be applied to the end of this shaft. Okay, and we are also going to solve for the torque, no, if the material or if the cross section of this same material is circular cross section. Okay, so we are going to compare the results, no, from our computations. Okay, so let's start solving this. Okay, so for this problem, we are going to solve the largest torque that can be applied to the end of the shaft with equilateral triangle cross-section. Okay, so class, to solve this torque, okay, so there can be two ways. So we can use the formulas, no, from the table. So we can use the formula for maximum shear stress. So we can compute the torque, no, from that formula, and we can also use the angle of twist, the formula for angle of twist, okay, to solve for torque. Okay, so class, we will compute both of the maximum shear stress and the angle of twist, no. We are going to compute the torque, and from the results, okay, we are going to compare them. Okay, if what torque, okay, we are going to use, okay, as the largest torque. Okay, so class, here for our solution nga, no, so from the table 5.1, so for the maximum shear stress, so this will also be equivalent to the working stress, okay, or the allowable shear stress, okay. So this will be equal to 20T over A cube. Where in T, class, so T here, okay, so this is the internal torque. Okay, so this is an internal torque, no, and you can get that at any section here, no, along this shaft. Okay, so class, this internal torque, no, so this will just be equivalent, okay, to the applied torque T. Okay, so this will just be T over A cube. Okay, A here, class, so this is the side of the equilateral triangle. So take note, class, that for equilateral triangle, so the sides are all equal. Okay, so in this case, the side of the equilateral triangle is 1.5 inch. Okay, so from here, class, no, we are going to substitute the values. Okay, so for the allowable shear stress, that is 8,000 pound per inch squared, is equal to 20. T is unknown. Okay, so we are going to solve that over A. So A here, class, is 1.5 inch cube. Okay, so from here, class, no, we can already solve for the value of torque T. Okay, so 8,000 times 1.5 cube over 20, so that is 1,350 pound inch. So the unit for this, class, is pound inch, ha, since the unit that we use here is pound inch. Okay, so class, this is not yet the answer. So we still have to compute the torque, okay, using the formula for angle of twist. Okay, so from table 5.1 again, so for the allowable angle of twist, so the formula is 46 TL over 8 to the 4th G. Okay, so L here, so the length is 4 feet. Okay, and G, this is given in the problem. Okay, so also the allowable angle of twist, it's also given in the problem. Okay, so the given in the problem for the theta, okay, is 0.02. Okay, and then this will be equal to 46 times T. So T is unknown. And then L, so this is the length of the shaft. So in this case, class, this is 4 feet. Convert it to inches, so that will be 4 times 12. Okay, so that will become 48 inches. Over A, so that is the side again of the triangle, which is 1.5 inches. So that is to the 4th. Okay, times G. So the given G class here, no, the material is given, right? So from the table for mechanical properties of some materials, no. So this is in English system or US customary unit. Okay, so the modulus of rigidity or shear modulus of the material given is 3.7 times 10 raised to 6 pound per inches squared. Okay, so from here, class, now we can solve for t. So solving for t, this is just 0.02 times 1.5 to the 4 times 3.7 times 10 raised to 6 over 46 times, okay, over 46 times 48. So the answer for this class is 169.67 pound inch. Okay, so class, from these two values of torque T, okay, we are going to compare them, class, and we are going to use the lowest value of T. Okay, so we are going to use this. So T is equal to 169.67 pound inch. So class, the reason is because, class, if we are going to use the larger value, okay, so if you are going to use this larger value, if you are going to substitute this value to the t here, no, for the allowable angle of twist, class, what will happen is that this allowable angle of twist, okay, it will exceed 0.02. Okay, so that is not allowed, no? The only allowable or the maximum angle of twist is 0.02. So that will exceed, no? So so in this case, class, no, we are going to use this lower value. And class, if you are going to substitute this lower value here, it's okay because it will not exceed this allowable shear stress. Okay, so for this instance, class, okay, so the torque is limited due to the angle of twist. Therefore, the largest torque or the largest allowable torque that can be applied, okay, to this shaft is 169.67 pound inch. Okay. Now, for the second part, class, now we are going to solve the torque that can be applied to a shaft of circular cross-section made from the same amount of material. Class, here, the cross-section here is equilateral triangle. So, class, what if the cross-section here, okay, is not an equilateral triangle? Let's say this is a circular cross-section with the same amount of material. Okay, so let's say for the area, okay, of the triangle, that should be equal to the area of the circle so that it will be the same amount. Okay, so class, for the area of the circle, okay, so the unit for the area of circle, that is pi r squared, right? And for the area of an equilateral triangle, so that is actually 1/2 base times height. So the base here is 1.5 and the height here, class. So the height here, okay, so take note, class, that the angles, all the angles for equilateral triangle, they are all 60 degrees. Okay, so the height here, class, so this will be the height. Okay, so this height, so from this right triangle, okay, so this will just be 1.5 is the hypotenuse, okay, and then the opposite side is the height, no? So that's what we need. Okay, so sine 60 degrees, that is opposite over hypotenuse. Okay, so solving for the opposite side, which is the height, so that will just be sine 60 degrees times the hypotenuse, which is 1.5. Okay, so that will be the area of the triangle, 1/2, 1.5 times 1.5 sine 60 degrees. So from here, class, now we can solve for the radius of the circular cross-section. Class, here we are going to, we are going to convert this equilateral triangle cross-section into a circular cross-section. So the radius of the converted circular cross-section, so that will be 0.5569 inch. Okay, so from here, class, okay, we can now solve for the torque that can be applied, no, using the formula for maximum shear stress and or allowable, and we can also use the angle of twist, Okay, so we have the same given for this class. So the only difference here is the cross-section. So it's now a circular cross-section. Okay, so for the shear stress, okay, so the allowable shear stress class for circle. So this is a circular cross-section already. So the maximum shear stress, this is equal to TR over J, right? So from here, class, no, so the same allowable stress, so that is 8,000 pound per inch squared. So this will be equal to T times the radius that we computed here, that is 0.55689 inch, over the polar moment of inertia J. So for the polar moment of inertia J, that is pi over 2 radius to the fourth. Okay, that's why it becomes pi 0 times 0.55689 inch to the fourth over 2. So we can now solve for the torque T here. So solving for torque T, so this is equal to 2,170.3. So the unit is pound inch. So this is not yet the answer, class. We still have to solve for the value of torque using the allowable angle of twist. Okay, so for the formula, class, for circular shafts, okay, take note, class, this is already a circular shaft. So the formula for the angle of twist is TL over JG. Okay, so from here, class, the allowable angle of twist is 0.02. So this will be equal to T times L. So the length, class, here is 4 feet. So converting it into inch, that will be 4 times 12. So that will be 48 inch. Over the polar moment of inertia, class, that is pi times 0.55689 inches to the fourth over 2 times the shear modulus, or the modulus of rigidity, that is 3.7 times 10 raised to 6 pound per inch squared. Okay, so solving, class, for the value of T, or the torque, so that is 232.91 pound inch. Okay, so from here, class, now we are going to compare the computed value for values of T, no, from the maximum shear stress and from the allowable angle of twist. Okay, so class, we are going to use, no, the smaller value here. Okay, so this is the allowable torque, no, that can be applied to the circular shaft, okay, having, ayun nga, circular cross section. Okay, so again, class, now we are going to use this because if you are going to use this torque, no, and substitute that here, no, so the allowable stress, it will not exceed 8,000 pound per inch squared, right? So again, the angle of twist, it limits the applied torque. So therefore, the torque to be applied is 232.91 pound inch. So this will now be the answer. And class, from here, no, we can compare the result, no, for circular, okay, and for equilateral triangle cross section. Okay, so class, it can be seen here, class, that a shaft of circular cross-section can support 37% more torque than the one having a triangular cross-section. Right? So as you can see here, class, this is the same amount of material. Okay, but the circular cross-section, it can handle a larger torque. Right? So that's why, class, this is the most efficient, no? So this is more efficient cross section than an equilateral triangle cross section. Okay. For sample problem number 2, determine the largest torque that can be safely applied to the rectangular steel bar if the maximum shear stress is limited to 120 megapascal. So that is for letter A. Now for letter B, compute the corresponding angle of twist using shear modulus G equal to 80 gigapascal for steel. Okay, so class, for this problem, no, so this is a rectangular cross section. Okay, so for rectangular cross section, we have formula to solve for the maximum shear stress and also for the angle of twist. And for the formulas, class, no, we are going to need, no, the values of the coefficients from this table. So we are going to use this table. Okay, so let's solve this, class. Okay, so for this problem, we are going to solve for the largest torque. Okay, and the angle of P. So solving first for the largest torque. Class, we are going to use here the formula for allowable shear stress. Okay, since it's given in the problem. So from the formula of allowable shear stress, since that is given, now we can solve for the value of torque T. Okay, so class, the formula for the maximum shear stress, this is T over C1 AB squared. So shear stress, the maximum shear stress or the allowable shear stress, this is given. Okay, and class, here T is the torque that we are going to solve. And then A and B here, class, so these are the dimensions of the rectangle. So again, class, A here, okay, so this is the larger dimension. So in this case, A here, class, is 20 millimeter. And then B here is the 6 millimeter. Now, for C1, so this C1, class, this is a coefficient that we can get from this table. Okay, so to get for the coefficients C1 and also for C2, class, no, so we have to solve first, okay, the ratio A over B. Okay, so solving for the ratio A over B. Again, A, that is the larger dimension, so that is 20 millimeter, over B, so that is the shorter dimension, which is 6 millimeter. So in this case, A over B, class, this is equal to 3.33. Okay, so from here, class, no, we are going to trace this value or look for this value at this column from the table. Okay, so class, as you can see here, there is no exactly 3.33 value here, right? So we have here 3, we have here 4, but there is no 3.33. So in this case, class, no, since 3.33, that is located between 3 and 4, so we are going to perform interpolation here. Okay, to solve for C1, okay, C1 and C2. Okay, so we are going to perform linear interpolation. Plus, if we are going to graph, okay, to graph this values in this table, no, so class, the graph here is aligned. Okay, so since it will be aligned, class, no, so we will perform linear interpolation. So performing linear interpolation, that will just be this value minus this value over this value, okay, over this value minus this value equal to this value minus this value over this value minus this value. Okay, so this is just like ano, class, this is just like a slope. Okay, so we just equated two equal slopes here. Okay, so for the first slope, that will be C1 minus 0.267 over 3.33 minus 3. Okay, so this will be equal to 0.282 minus 0.267 over 4.0 minus 3. Okay, so that's how you do interpolation, class, ha? Okay, so from here, class, now we can solve for C1. And the value of C1 here, class, is 0.272. Okay, now solving for the value of C2, so we are now going to use these values. Okay, so again, 3.33, that is between 3 and 4. So the value of C1 will also be between this and between this and between this and between this. So as you can see, class, for C1, so the answer is 0.272. So you can check that, no? So this value, so this is logical naman since this is between 0.267 and 0.282, right? Okay, and also, class, for C2, so to solve for C2, that is just C2 minus 0.263 over 3.33 minus 30. So that will be also equal to 0.281 minus 0.263 over 4 minus 3. Okay, so the value, class, of C2 here is 0.269. So this value, class, so this is between 0.263 and 0.281. So we can say that this is logical values naman. Okay, so from here, class, now we can already use these values, no, and substitute here in this formula. Class, substituting the values here for the maximum shear stress that is given in the problem. So that is 120 Newton per millimeter squared. Okay, so this will be equal to T over C1. Our C1 is 0.272. And then our A, that is the larger dimension of the rectangle, so that is 20 millimeter. And B here, class, is the shorter dimension, which is 6 millimeter. And this is anaha squared. Okay, so from here, the only unknown, class, is T. So we can solve for the value of T. So solving for the value of T, that is just actually 120 times 0.272 times 20 times 6 squared, no? So the answer for this class is 23,500.8, and the unit for this class is Newton millimeter, ha? Okay, so class, this will now be the answer. So class, here, the angle of twist is not given. Okay, so we cannot compare values of T here since there's no value of angle of twist. So here, class, this is already the answer. Okay, so based on the allowable shear stress given in the problem. So the largest torque is 23,500.8 Newton millimeter. Now, for the angle of twist, class, the formula, okay, for rectangular cross-section, that is TL over C2 times AB cubed times G. Okay, so C2 here, class, we already solved for this coefficient, and the value is 0.269. Okay, so from here, class, the only unknown will be the torque T. So, the theta rather. So, we already solved pala, class, for the torque T. So, solving for the angle of twist, this will be equal to T. So, the T here, class, is 23,500 Newton millimeter. And then the length here, class, it should be in millimeter, ha, since we use millimeter here. So, we should be consistent. So, the length, class, is 800 millimeter. Over the coefficient, 0.269. And then the value of A here, class, which is the longer side, is 20 millimeter. And the shorter side, which is B, that is 6 millimeter. So that will be cube. Times the G. Okay, so class, here, G, or the shear modulus, this is 80,000 Newton per millimeter squared. So class, solving for the angle of twist. Okay, so the angle of twist here, class, is 0.20223 radian. So this will now be the answer. So this will now be the answers for this problem, class. We are already done in our discussion about torsion of circular and non-circular solid shaft. So we are now going to proceed to our discussion about torsion of thin-walled tubes. Thin-walled tubes, class, these are hollow tubes. So meaning to say there is a hole in the cross-section, okay, of these tubes. Okay, so although torsion of non-circular shaft requires advanced methods of analysis, fairly simple approximate formulas are available for thin-walled tubes. Okay, so there are already established formulas also, class, no, for the torsion of thin-walled tubes. Such members are common in construction where lightweight is of paramount importance, such as automobiles and airplanes. Okay, so there are instances, class, no, that we prefer thin-walled tubes, okay, to use, no, rather than solid shafts. Okay, so the reason for that is because since hollow tube, so there is a hole in the cross section, so meaning to say it will be lighter in weight compared to shafts or tubes that are solid in cross section. Okay, so that is the advantage for this. Now this is lightweight. Okay, so plus, let's consider the thin-walled tube subjected to the torque shown in the figure. So let's say we have here this thin-walled tube. So this is thin-walled, and this is hollow. Okay, so there is a hole, okay, in its cross-section. So its thickness is T. Okay, and class, this broken lines that you can see here, no? So this indicates the middle surface. Okay, so this is these broken lines, these are lines at the middle, okay, of the thickness. Okay, so class, this middle surface, this is the area, no, between the outer and the inner wall, okay, of this tube. Okay, so class, here, no, if the thickness T, if it is very small compared to the overall dimensions of the cross-section, the shear stress, okay, induced by torsion can be shown to be almost constant through the wall thickness of the tube directed tangent to the middle surface. Okay, so class, the shear stress here, again, okay, so the shear stress here in the thickness okay, of this thin wall tubes. This is actually the cross section here, di ba? The cross sectional area, since there is a hole in the middle, no. So class, the stress, the shear stress, it will be induced, okay, in the thickness of the of this thin wall tube. Okay, so that shear stress, class, that is again almost constant, okay, in its middle surface. And class, it is ano ha, it is tangent. The shear stress that is tangent, no, to this middle surface. Okay, that is tangent here. Okay, so class, it is um, convenient to introduce the concept of shear flow, denoted by Q, defined as the shear force per unit edge length of the middle surface. Okay, so class, the shear flow, this is the amount of shear force, okay, that flows, okay, in the middle surface. Okay, so plus the unit for shear flow, okay, so that is Q is equal to shear stress times the thickness. Okay, so from this formula, class, no, this result states that the product of the average shear stress times the thickness of the tube, or the shear flow, no, that is the same at each point on the tube's cross-sectional area. Okay, so the shear flow, the shear stress, that is the same or constant at each point on the tube's cross-sectional area. Okay, take note of that, class. Okay, so also, class, no, if you're going to analyze this formula, no, we can observe from this, no, that if the thickness, okay, if we have a let's say thicker wall, okay, if we have a thicker wall, what happens to the shear stress is that it decreases, right? Or yeah, if T is a large value, plus what will happen, it will Q will be divided by that thickness. Okay, and the more that the value of the thickness increases, no, the more that the shear flow, it will decrease. Okay, so in the same manner, class, no, the shear stress will also decrease. Okay, so class, but on the other hand, if the thickness is very thin, so if the value of the thickness is very small, what happens is that the shear stress will increase. Okay, it will increase. So that's the relationship, no, of the formula here. Again, class, if the thickness, okay, has a large value, the shear stress will decrease. Okay, on the other hand, class, if the thickness is very thin, okay, if it has a very small value, okay, the shear stress, it will increase. Okay, so take note of that, class, of that relationship. Okay, so let's talk about now the average shear stress, or the shear stress on the cross section of a thin wall tube or hollow tube. Okay, so class, the formula for this is already established. So the derived formula for this, class, is equal to T over 2T times A sub M. Okay, so let's say we have here this thin wall tube. Okay, so this is the thickness. Okay, and this broken line, class, no, it indicates the center line, or the middle line. Okay, so this is at the middle, okay, of the thickness. Okay, so class, from here, no, from this formula, the tau average, that is the average shear stress acting over a particular thickness of the tube. Okay, and then T here, class, this is the resultant internal torque at the cross section. So this is ano ha, this is internal torque. So you have to solve this using equilibrium equation. Okay, and then for T, that is the thickness of the tube, where the shear stress is to be determined. Okay, and lastly, for A sub M, so A sub M, class, this is the mean area enclosed within the boundary of the center line of the tube's thickness. So this A sub M, class, no, this is shown here in this shaded region. Okay, so this is the area enclosed by the center line. So that is the area or AM, okay, that we are talking about here, ha. Okay, and also, class, no, from this formula, since we know that the shear flow Q is equal to shear stress times thickness, then the shear flow throughout the cross section, no, considering this formula, Okay, so if you are going to substitute shear stress times thickness, no, if we cross multiply this, so this will be shear stress times T equal to T over 2am. So that shear stress times T, that is equal to Q. Okay, so meaning to say the shear flow, its formula can also be T over 2 times A sub M. Okay, so take note, class, of these formulas because we are going to use all of this, no, in our computations. Okay, now for the angle of twist. Okay, so the formula for the angle of twist, class. So this is equal to TL over 4 times AM squared times G times the line integral of ds over T. Okay, so class, here, so T, again, this is the internal torque. Okay, so you have to solve that using equilibrium equation. And then length here is the length of the thin wall tube. And then AM here, so just like we talked about, no, in the formula for the shear stress. So this is the same area. So this is the mean area enclosed within the boundary of the center line of the tube's thickness. So this is shown here, no, in this shaded region. Okay, so also, class, no, G, this is the shear modulus or the modulus of the material of the thin wall tube. Okay, and then class, for this line integral ds over dt. Okay, so this is the summation of the length of the median line in the mean area over the corresponding thickness. Okay, so class, this median line, so this is the broken line here. Okay, so again, this is the line at the middle, okay, of the thickness. So class, the length of these broken lines, okay, we have to solve them. Okay, so let's say for a circle, so the length of that of the circle, the length of the curve of the circle, that is actually the circumference, or 2 pi r. Now for shapes like um rectangle, square, triangle, or any other shape that is composed of a straight line. So to solve for the length of the median line, that is just the perimeter. Okay, the perimeter of the shape. Okay, and plus it should be ano ha, it will be divided by thickness. So that is the corresponding thickness for that median line. Okay, so there are also cases kasi, class, that for that median line, so there's a different thickness for that portion, and then for the other median line, there is another corresponding thickness. So we have to consider that. Okay. For sample problem number 1, calculate the average shear stress in a thin wall tube having a circular cross-section of mean radius equal to 5 inches. So mean radius, class, this is the radius from the center of the cross-section to the median line. Okay? And then thickness equal to 0.12 inches, which is subjected to a torque T equal to 320 kips inch. Also, what is the relative angle of twist if the tube has a length of 14 feet? So use shear modulus equal to 11 times 10 raised to 6 PSI. Okay, so again, class, we are going to solve for the average shear stress and the angle of twist using the formulas that we talked about. Okay. Okay, so to solve this problem, class, no, for the average shear stress, okay, so using the formula, so this is equal to T over 2 times T times A sub M. So we have to solve first for the A sub M. So this is the mean area enclosed by the center line. Okay, so in this case, class, no, the given radius here is the mean radius. So that is the radius from the center to the center line. Okay, center line in the thickness. Okay, so that is RM. So class, we know that for a circular or for a circular shape, okay, so the formula for its area is pi r squared. Okay, so to solve for the area, okay, or the mean area enclosed by the median line, which is a circle, so that will just be pi r sub m squared. Okay, so from here, class, no, we can now substitute the values or the given values in the problem. Okay, so for the torque, no, so the applied torque, class, is 320,000. So if we are going to solve for its internal torque, no, at any section here, okay, so using equilibrium equation, so that will just be equal to that applied torque. So that will just be 320,000 pound-inch over 2 times T. So the T here, class, is the thickness, which is also given. So that is 0.12 inch. And then times the A sub M. So A sub M, pi Rm squared. Okay, so Rm, class, this is the mean radius. So that is given in the problem. So that is 5 inch. And this will be squared. So solving for the average shear stress, so this is simply 16,976.53 PSI. Now for the second part, that is for the angle of twist. So the formula for angle of twist is equal to TL over 4 AM squared times G. And then we have here line integral ds over T. Okay, so from here, class, we already know the value of AM, or the formula is this, right? So that is the formula for A sub M, or the mean area. Okay, and then G, this is the modulus of rigidity. So this is given in the problem. So the length, class, the length is also given in the problem, right? Okay, now, class, to solve for this, we have to solve first for this line integral ds over T. Okay, so, class, again, no, for the line integral ds over T, so this is just the summation, okay, um, of the length, okay, of the center line, okay, over its corresponding thickness. So in this case, class, the length of the middle line, okay, the length of the middle line, class, this is a circle. Okay, so the length, class, is the circumference of the circle. Okay, so, class, the circumference, the formula is 2 pi r. Okay, so in this case, class, the r here, class, should be the mean radius, which is 5 inches. That is given in the problem. Okay, so from here, class, no, so again, ds, so that is the length of the middle line, which is 2 pi r sub m over its corresponding thickness. Okay, so, class, substitute lang natin. Let's just substitute the value for this, no, here in our formula. Okay, so theta, class, will be equal to T. Our T here, class, is 320,000 pound-inch times the length. So the length here, class, is, if converted in inches, that is 168 inches over 4 times A sub M. So A sub M, class, is this value, no? So that is pi times Rm, which is 5 inch squared. And then don't forget, class, that this AM is squared, ha? So you have to square it here further. And then times the modulus of rigidity, which is 11 times 10 raised to 6 pound per inches squared. Okay, and then the value for this, class, okay, so this is 2 pi times R sub M, which is 5 inch over the thickness, which is 0.12. Okay, so from here, class, no, class, take note, class, ha, that your units here should be consistent, ha. So as you can see here, all of the units here are in pounds and inch. Okay, so, class, the answer for theta, so this is the angle of twist, it will be in radian. Okay, so the answer for this, class, is 0.051856 radian. Okay, so, class, these are now the answers, ha, for this problem. Okay, so for sample problem number 2, the tube is made of C86100 bronze and has a rectangular cross-section as shown in this figure. Okay, so this is the cross-section, class, of this tube. Okay, so this is a hollowed or thin-walled tube. Okay, so if it is subjected to the two torques, so this is the torque, no? So this is 60 Newton meter, and we also have here this applied torque. So this is 25 Newton meter. Okay, so determine the average shear stress in the tube at points A and B. So points A and B, they are located here, no, at this section. And then, what is the angle of twist of end C? Okay, so there will be an angle of twist here at end C, so we have to compute that. Okay, so this E, okay, so this end E, this is supported by this fixed support. Okay, so from here, class, no, as you can see in the cross section, so the tube, its thickness, no, at this side, so this is 5 millimeter. So both for this side and this side, their thickness are 5 meter. Okay, and for this side and this side, okay, so the thickness here, class, is 3 millimeter. They are both 3 millimeter. So we have here different thicknesses for the top and bottom and the left and right. Okay. Okay, so let's try solving this, class. Okay, so for this problem, class, we are going to solve the shear stress in the tube at points A and B. So again, class, point A and B, they are located, no, at this section. Okay, so class, they are actually at one cross section. Okay, point A and point B. Okay, so to solve for the shear stress at these points, okay, so we have to determine the torque acting at this section. Acting at this section. Okay, so also, class, no, since point B is at this point and then point A is here, no, so the thickness at point B is actually 3 millimeter. Okay, and the thickness for point A, that is actually 5 millimeter. Right, so they have different thicknesses, so they will have different shear stress. Okay, so the formula for shear stress is actually T over 2 times thickness times A sub M. Okay, so we have to determine first, class, no, the torque, no, acting, no, or the initial torque, no, here in this cross section. Okay, so class, if you are going to cut, no, a section that passes through this point, okay, so this will be the cut section. So we will consider this segment. Okay, so considering this segment, we have here this torque, 60 Newton meter, and this torque, 25 Newton meter. So our internal torque here, let's say it will be clockwise, no? Clockwise, so that is clockwise, right? That is clockwise. Okay, so we will assume that the direction of our internal torque T is clockwise. Okay, so from here, class, we can solve this internal torque by equilibrium equation. Okay, so summing up all the torques here, so equal to 0. So our assumption here, class, is for torques that are clockwise, that will be negative, and for torques that are counterclockwise, that will be positive. Okay, so summing these torques, summing them up, so for the 60 Newton meter torque, so this is positive since this is counterclockwise. Right, and then minus 25 since this is counterclockwise, and then minus T since our assumption also here is clockwise. So from here, class, no, we can solve for the value of T, and the value of T here, class, is positive, meaning to say we have the correct assumption that the internal torque T is clockwise. Okay, so the value of T, class, is 35 Newton meter. So take note, class, that this internal torque, this is the torque, no, at the at points B and A, or at the cross section wherein points A and B are located. Okay, so this is the torque that we are going to use for the computation of the shear stress in this cross section. Okay, so class, also to solve for the shear stress, we need the value of A sub M. So that is part of the formula. So A sub M, that is the mean area, no, enclosed by the center line. So in this case, class, no, if you are going to establish the center line, okay, so the center line here will be the center, class, of this 3 millimeter thickness is 1.5. So this is 1.5, and then also here 1.5. 1.5 is the inner thickness. Okay, from the center line to the inner wall, so that is 1.5. Okay, also here, class, no, at the in the walls here at the left and right, so these are 5 millimeter thick wall. Okay, so class, here the center line will be 2.5, no, 2.5 from the center line to the inner wall. Okay, and also here from the center line to the inner wall, that is 2.5. Okay, so from here, class, no, we can solve for the mean area. So for the mean area, class, so the that will be the enclosed area, no, by these center lines. Okay, so class, this center line, okay, so let's say this width. Okay, so this is actually 35 millimeter. So this came from 40 millimeter minus the thickness here, the thickness from the center line to the outer wall, that is 2.5. So we will subtract that. And same here at the other side. So we will subtract the thickness from the center line to the outer wall. So that is also 2.5. So that will be 40 minus 2.5 minus 2.5. That's why it became 35 millimeter here. Also for this height, okay, so class, this is 60 millimeter minus 1.5. Okay, the outer thickness here minus 1.5 for the outer thickness also here. So that will be 60 minus 1.5 minus 1.5. That is 57 millimeter. And from this dimensions of this rectangular center lines, okay, so the area here, class, will just be 57 millimeter times 35 millimeter. So this will be the area. So the area here, class, is 1,995 millimeter squared. Okay. So from here, class, no, we already know the internal torque T. We already know the mean area. So we can now solve for the shear stress at point A and point B. So starting with point A. So at point A, class, the thickness of the wall here is 5 millimeter. Therefore, class, applying the formula here, so the formula for shear stress at point A is equal to T over 2 times thickness times the mean area. So substituting the values here, for the internal torque, that is the computed torque, class, that is 35 Newton meter. Okay, so since this is in meter, now we will convert this meter into millimeter. That's why it becomes 35,000 here over 2 times the thickness at point A is 5 millimeter times the mean area. So the mean area, class, is 1,995 millimeter squared. So be consistent, class, how with the units here. So from this, no, we can compute it now, class, no. So the value, class, of the shear stress at point A is 1.7544 megapascal. Okay. Now, for the shear stress at point B, okay, so we will also solve this. So this stress will be different, no, from the shear stress at point A because they have different thickness. So the thickness at point B, so the thickness of the wall at point B, class, is 3 millimeter. Okay, so this is the thickness that we're going to use in our formula here. So we will just apply, class, or substitute the values for T, which is 35,000 Newton millimeter over 2 times the thickness, which is 3 millimeter, times the mean area, which is 1,995 millimeter squared. So from here, class, now we can now compute the shear stress at point B. And this is 2.9240 megapascal. So this will now be the answers for the first part. So we still have this second part, so we will also solve this. Okay, so for the part 2 of the problem, we are going to solve for the angle of twist of end C. Class, as you can see here, no, in this given tube, no, with these torques. Okay, so class, from point C to point D, okay, so there will be an angle of twist here, and there will also be a different angle of twist from point D to point E. Okay, since they are subjected, no, to these torques. Okay, so if you are going to cut a section from point C to point D, so there will be an internal torque for that. But if we cut a section here, class, no, from D to E, any section here, class, so if you are going to cut a section here, class, there will also be a different internal torque. Okay, so from here, class, no, we can solve for the angle of twist by combining the angle of twist from point C to point D and from point D to point E. Okay, so to solve this, class, no, the angle of twist, no, of length CD and length DE. So we have to solve first for the internal torques. Okay, so for the internal torques class, so this is the free body diagram to solve for the internal torque. So let's say for the internal torque at DE. Okay, so the internal torque here class, so this is the same internal torque as the torque that we computed, no, from the part 1 of the problem. Okay, so we can just say that the internal torque at length DE, so that is just 35 Newton meter as we computed from part 1. Okay, now for the internal torque in length CD, so if we cut a section here class, so let's say this is the cut section. So the internal torque here will be this torque, and then if we apply equilibrium equation here class, obviously our torque, which is, or the internal torque at CD, that is equal to 60 Newton meter. And our assumption here class is clockwise. Okay, and the answer here class will be positive since the other torque here class is negative, right? So this reaction torque, or internal torque, it has to oppose that applied torque, which is 60 Newton meter. No? So our internal torque here class will be 60 Newton meter. Okay, so from this internal torques class, no? Okay, so we have to follow. Okay, since we are going to sum up all the angles of twist, no, the angle of twist from CD to DE, class, we are going to apply here the sign convention, okay, which we discussed, no, in the introduction of this topic about torsion. So class, for summation of internal torques, or for the angle of twist, okay, so our convention is it depends class, it depends on the double-headed arrow. Okay, the direction of the double-headed arrow, which represents the torque. So in this case class, let's say for TCD, for this torque at CD, so class, this is actually, let's say the cross section is here. The cross section is here. Okay, and the rotation class of torque CD is clockwise. So the rotation is clockwise. So this is the clockwise rotation, right? Okay, so from here class, no, this thumb, which represents the double-headed arrow, this is pointing away, no, from the cross section. Okay, so meaning to say class, the torque, or the angle of twist for the torque CD, that is positive. Okay, or the internal torque itself, that is positive. Okay, same here class, no, for the torque at length DE. Okay, so this is also clockwise, right? Clockwise, and then the cross section is here, so clockwise, plus your thumb, or our thumb, which represents the torque. Okay, this is pointing away from the cross section. Okay, so meaning to say class, this is also positive. Okay, so both of these internal torques class, if we sum up the angle of twist, they are both positive, ha? Okay, so they are both positive. So let's now apply class, no, yung solution, our solution to solve for the angle of twist. Class, for the angle of twist, no, for the solution for hollow tubes, no, we have this term, no, in the formula. So this is line integral ds over dt. So this is the summation. Okay, so this is the summation of the length, no, of the center line, or the middle line, okay, in the mean area, okay, over its corresponding thickness. Okay, so in this case class, let's say for this middle line, no, so this middle line, so this is 57 millimeter, and this is also 57 millimeter here. Okay, so this middle lines class, their corresponding thickness are 5 millimeter. So they are both 5 millimeter, right, the thickness. So this will be 5 millimeter here. And plus the summation of the length of this middle lines will be, it's just 57 millimeter plus 57 millimeter, which is 2 times 57 millimeter. Okay, and also class, for these middle lines, okay, this middle line and this middle line, they have the same thickness as well, right, which is 3 millimeter. So class, the summation of these middle lines, no, so this is 35 millimeter, so 35 plus 35 millimeter, or 2 times 35 millimeter, over their corresponding thickness, which is 3 millimeter, ha? Okay, so solving this class, so this is actually 46.133. So we can just substitute it, ha, to this term, no, in the formula. So solving for the angle of twist class at NC, so we will just sum up the angle of twist of CD and DE. Okay, so solving for the angle of twist class, so that will just be this summation. So they will both be positive, ha? They are both positive based on our sign convention. Okay, so following the formula class to solve this, so for the angle of twist of DE, so this is DE. Okay, so T, that torque here class is 35,000 Newton millimeter times its length. So the length of DE is 1.5 meter. So that will be 1,500 in millimeters. Over 4 times AM. So class, this is the same AM, no, that we computed in part 1. Okay, so that is 1,995 millimeters squared. And don't forget, class, that this is squared. So we will square this further. And then for the shear modulus, that is 38,000 Newton per millimeter squared. So this is given in the problem. Or if it's not given in the problem, the material is given, right? So we can look for the shear modulus for that material in the table, right? For mechanical properties of some materials. Okay, so in this case, this is in SI unit, okay, or metric system. No? So you can look for that shear modulus at that table. Okay, times the line integral ds over dt, we already computed for that. That is 46.133. Okay, that is just for DE. Okay, now for CD, the angle of twist of CD, that will be 60,000. Okay, so that is the internal torque, no? Internal torque T of here, no, at length CD. So that is the computed torque here. Okay, times its length. So the length of CD class is 0.5 meter, which is 500 in millimeters. Okay, and then from here class over 4 times AM, so that is again 1,995 millimeters squared. So don't forget to square that also, times this is the same modulus of rigidity, that is 38,000 Newton per millimeter squared. And for the line integral ds over dt, that is also the same, which is 46.133. Okay, so from here class, we can now compute for the angle of twist. So solving for the angle of twist, this is equal to 0.006291 radian. Okay, so this will now be the answer for part 2 of this problem. So that concludes our discussion for this topic. I hope that you learned and attained the learning outcomes. Okay, so I'll see you again, class, on our next meeting. Keep safe and God bless. Bye-bye.